Hi, welcome to my channel. I am Aravinthan. In this video, I'm going to discuss questions related to electric field from Cambridge past papers. So I made a worksheet from selected questions from different past papers, and the worksheet is uploaded in the Google Drive, and you can download it before watching this video. The instruction for downloading is given in the description part of this video. So please go to the description part of this video. There you can get the link or the URL to download this particular worksheet. Okay, all the questions are from Cambridge past papers. Right, okay, first question. It says A part. State one similarity and one difference between the electric field lines and the gravitational field lines around an isolated positively charged metal sphere. Okay, gravitational field lines, both electric field lines, both are radial. Is it? Both are radial field. And you know, when the distance increases, the gap between the field lines will increase. So that is the similarity. The differences, the gravitational field lines will be directed or pointed towards the sphere, but this is positively charged sphere, so the electric field lines will have arrow or the direction away from the sphere. That is the difference. So they ask you to state one similarity and one difference. So I gave the answer for them. Right, okay, B part. Now they have given this diagram as figure 6.1 in that question. So here it stated a positive point charge plus Q is positioned at fixed point X, and an identical positive point charge is positioned at fixed point Y, okay, as in figure 6.1. The charges are separated in a vacuum by a distance of 10 centimeters. So the 10 centimeters is the gap distance between X and Y. Points A and B are on the line XY. So you can say line XY is drawn. On that line XY, there are 2 points A and B, and their distances are given. From X, 2.5 centimeter A. From Y, B is at a distance of 2.5 centimeter. So point A is at a distance of 2.5 centimeter from X, and point B is at a distance of 2.5 centimeter from Y. The electric field strength at point A. So at point A, the electric field strength is given, that is 4.1 into 10 to the power minus 5 volt per meter. You know, Newton per coulomb and volt per meter refers the same thing. They indicate the unit. They are the unit of electric field strength. Calculate the charge plus Q. So Q is an unknown. So you know electric field strength is a vector quantity. The resultant electric field strength at A is given. So I can say E A, electric field strength at A is given. How much is it? 4.1 into 10 to the power minus 5 volt per meter or Newton per coulomb, both same, right? Okay, that's the electric field strength. So we need to find the values of Q, both are having the same magnitude. Okay, so you know the electric field strength due to the charge at point X will be towards right. I already told in my previous videos, mainly in my first video I told, keep a positive test charge. When I keep a positive test charge at A, the plus Q will repel. So the direction of the electric field strength due to this charge at A will be E1, I can say, towards right. Same way, the direction of the electric field strength due to this charge at A will be towards left, because if I keep a positive test charge at A, this will repel. I already told that direction of the electric field strength is defined as the direction of the electrostatic force acting on a positive test charge. So E2, that's the electric field strength of Q at Y towards left. Okay, so they are saying the direction of the electric field strength at A is given as 4.1 10 to the power minus 5, but obviously I know that certainly even greater than E2 because it's closer, point A is closer to X. So I can say the resultant electric field strength at A, EA, is equal to E1 minus E2 because both have the same magnitude, right? And A is closer to X than Y. So this will be larger than this one. So EA is given. We know that 4.1 10 to the power minus 5. E1 is, I can say KQ over R squared. So I'll substitute as R squared minus KQ over R. I can say R1 squared, this as R2 squared. R1 is 2.5. R2, I need to calculate this length. We can calculate it 10 minus 2.5. This length is 10 minus 2.5. Okay, it should be in meters. Okay, so we'll substitute the values. We know the K, that is 9 into 10 to the power 9. And I can take the even Q out. Is I can take the value of Q also out. Yeah, out of the bracket Q. 1 over R1 is 2.5 centimeter. Convert to meter 0.025 all things squared minus 1 over the distance of A from Y is 10 minus 2.5, that will be 7.5. So 0.075 squared, that is equal to 4.1 10 to the power minus 5. Solve it and get the unknown Q. So you will get answer for Q, that is equal to 3.2 10 to the power minus 18 coulomb. Okay, so now we are going to consider the first question, B part, second part. Okay, so there you can see they are saying like this on figure 6.2, sketch the variation of electric field strength E with distance D from A to B. So they are measuring from A to B. So you know the distance from A to B is 5 centimeters because totally 10 centimeter. This is 2.5, this is 2.5. So this will be 5 centimeter. So they are analyzing the variation of electric field strength from A to B, right? And this grid is given on the paper as figure 6.2. This grid is given. I'm doing the question 1. You can download the paper from the Google Drive, go through the description part, all the instructions are given, right? Okay, so you can, this graph paper, the grid is given, right? So they ask you to draw the shape of the electric field strength measured from distance A to B, the variation. Okay, at A we know the electric field strength that is given in the first part of B part. That is given as 4.1 10 to the power minus 5. So on the grid you can start from 4.1. So 4.1, from that you can start the graph, right? Now you know that both are having the same magnitude of charge, both are positive charges. So exactly at the midpoint of X and Y, there will be a null point. So exactly midpoint will have a null point. So that is from that N will be at a distance of 5 centimeter from X. So from A, it will be at 2.5 centimeter. The electric field strength will be equal to 0 because X and Y have the same magnitude of positive charges. So at N, the electric field strength is 0, means I know one of the coordinates now at 2.5 centimeters. So somewhere here, 2.5 centimeter, the electric field strength is 0. So the graph starting from here, at this point, the electric field strength must be equal to 0. Now, when you go to B, A and B are identical points, is it? Because A is 2.5 from X, B is 2.5 from Y, and both are same magnitude of charges. So at A, I know the resultant electric field strength, which is 4.1, is towards right because E1 larger than E2. Now, same way when you consider point B, the electric field strength due to this charge will be larger than the electric field strength due to this charge at B. So at B also, the magnitude of the electric field strength will be same as the magnitude of the electric field strength at A because distance is same, right? But it's going to be towards left. So the graph is starting from positive. That means we are taking towards right. Positive means towards left should be negative. Okay. So at from A at B means that is at a distance 5, the electric field strength should be minus 4.1 minus 4.1. 10 to the power 5 is given, minus 5 is given as common. So the graph should be a decreasing gradient, then increasing gradient, decreasing gradient, increasing gradient up to distance 5 and the coordinate minus 4.1. This is 5. Okay, this is the answer for B part, second part. It's a decreasing gradient, increasing gradient graph. Okay, question 1, still we are doing part 3, B part, part 3. A small positive charge is placed at A. Okay, a small positive charge is placed at A. The electric field causes this charge to move from rest along the line AB. Describe the acceleration of the charge as it moves from A to B, a positive charge. I always told that earlier also I told that positive charge will experience electrostatic force along the direction of electric field lines. So you can see that from A to N is the null point, the electric field strength is decreasing, that is directed towards right. So the positive charge also will experience electrostatic force towards right until it until it reaches the point N. So beyond point N, the resultant of the direction of the resultant electric field strength will be towards left. So the electrostatic force will be towards left, but it gain a velocity up to N, right? We can calculate the velocity, but in this question it is not asked, but I did that in my previous work lessons. And in this paper also there are questions appeared in different years, we can calculate the speed at n. So that will be the maximum speed because until n it's going to accelerate. So where will it have the maximum speed? At the end of acceleration, the charged particle will have the maximum speed, but beyond n, until it reaches the point B, it will have velocity towards right, but acceleration towards left because resultant force is towards left. So whenever a particle has acceleration opposite the direction of velocity, it will decelerate. Okay, so what's going to happen? From A to the midpoint, it's going to accelerate and the acceleration will decrease. Why? The electric field strength is decreasing. F equal QE and F equal QE and MA. So electric field strength is decreasing. So acceleration will decrease, but the velocity will increase. Then at the center of AB, it will have the maximum velocity and zero acceleration because at that point electric field strength is zero, so no acceleration. Then from N to B, the particle will decelerate and the deceleration will increase. Or we can say it will accelerate in opposite direction to its motion, and that acceleration which is in opposite direction will increase. That is the answer for this third part. So they also describe the acceleration of the charge as it moves from A to B. So you can say from A to B, the acceleration will decrease and velocity will increase. At the midpoint of AB, the acceleration will be equal to 0. Then from midpoint of AB to B, the acceleration will again increase in opposite direction, or you can say it will decelerate from midpoint to B and the deceleration will increase. Okay, now we'll discuss the second question on my worksheet, page number 3. You can download the worksheet from the description part. Google Drive instructions are given. So please go to the description part of this video. Right. Okay, so second question, A part, state what is meant by electric potential at a point. That is actually, all of you know, that's one of the theory part. Work done in moving positive 1 coulomb charge from infinity to a point is defined as the potential at that point. Okay, work done in moving positive 1 coulomb charge from infinite distance to a point is defined as the electric potential at that point. So that's the A part of the second question. Okay, B part, this diagram is given there as figure 7.1, and they are saying a movable point P. So P is movable point P. So this is sphere A, sphere B, both are spherical shaped conductors. Movable point P lies on the line joining the centers of the two spheres. Point P is a distance x from the center of A. From the center of A, P is at a distance of x. The variation with distance x of the electric potential, they are going to create both a charge carrying, they are carrying charge, so they are going to create electric potential on this line. So at different points, the electric potential will be different. So x is measured from the center of the sphere. So this graph is given as figure 7.2 on the same question. So how the electric potential is varying is given. So it's given on a grid. You can see when you download the paper. But I marked only the important values, important coordinates of the given graph, right? So the question is, right. So first part of this question, B part of the second question. So that's the first part. Use figure 7.2, this graph, to state and explain whether the two spheres have charges of the same or opposite sign. Okay. Now, they are spheres, conducting spheres. So conducting spheres will have the same potential. When you consider a particular sphere, it's carrying charge, it's a conductor, solid sphere, not a hollow sphere, solid sphere. So when it carries charge on its surface, we know that the electric field strength inside the sphere is equal to 0 because it's a static charge. So the charges have already displaced and they are not experiencing any electrostatic force inside the solid sphere, conducting sphere. So inside the solid sphere, there is no electric field strength, but the electric potential will be the same at all points, and that will be the electric potential on the surface also. You can see up to 12 centimeters from the center of the sphere A, the electric potential is drawn constant. So obviously we know that radius of A is 12 centimeters. So because it's measured from the center O, the x is measured. So the electric potential on the surface is 2.4. This electric potential also positive. So in case if this is carrying a negative charge, certainly this voltage should be negative. Anyway, those are not in your syllabus. Even positive carrying two conductors, positive charges, if they carry, when you bring them, there is a chance they can attract, but that theory is not in your syllabus. But here, according to this data, both potentials, you can say this is the potential of this sphere, that also positive, this also positive. Since both potentials are positive, that means both are carrying positive charge. In case if this is carrying negative charge or this is carrying negative charge, there should be a negative potential, but there is no negative potential, so both are positively charged. So you can state the answer for question second question, B part, first part. You can say like this. On the graph, the potentials are marked only on positive axis. Therefore, both are carrying positive charge. Okay, you can mark like that. You can write like that. Since all the potentials are shown in this graph with positive value, that means both spheres are carrying positive charge. Okay, now question 2, the second question, B part, second part, we are going to discuss. So they are saying it, the question says that a positively charged particle is at rest on the surface of sphere A. The particle moves freely from the surface of A to the surface of B. So A to B is moving freely. So it's allowed to move freely, right? Describe qualitatively the variation, if any, with distance x of the speed of the particle as it moves from x equal 12 centimeter to 25 centimeter. So they ask you to describe how the speed varies for a certain range of distances. First range they are saying x equal 12 centimeter, x equal 12 centimeter to x equal 25 centimeters. So we need to explain or state and describe what is happening to the speed when it moves from 12 to 25, 12 to 25. So 12 to 25, somewhere here, 25 is this point. You can see the graph, 25 is sliding. The lowest point is marked at 26. So I'll explain it. Then it's at x equal 26 centimeter. What's happening to the speed? Then when it moves from x equal 27 centimeter to x equal 31 centimeter, that is 27 means somewhere from here to here, right? We'll see. Then x equal 32 centimeter. Okay, we need to answer 4 different parts, 4 marks each one. But if the small description and the statement are correct only, you will get that 1 mark. Okay, small explanation. Okay, now I can say like this. We learned that the electric field strength E is given by the potential gradient dV over dx. We know that. We can explain by using this, or we can explain by using work done equal QV, W equal Q times delta V. Either way I can explain. I'll first explain by using this. I feel this is easier than this one. Okay, if I use this one, E equal minus dV over dx. Potential gradient, this is called potential gradient. Please go through my previous video lessons. I think I explained this in the 8th video, I think. Yeah, E equal minus dV over dx, negative. So that means, you know, the graph is given V against x. So that means obviously the slope of the graph at any point gives the electric field strength at that point. Are you clear? So slope of the graph, if you draw a tangent at any point of the graph, right? The tangent, the gradient of the tangent will give the electric field strength at that particular point of x. Right. Now you can see, when you consider the slope of this shape of graph, that is when we consider 12 centimeter to 25 centimeter, that means this slope up to somewhere here, 25 centimeter somewhere here. So the slope is decreasing. How to find out the slope is decreasing? You can keep your ruler like a tangent, or you can keep your pen like a tangent, and you can see, move it. You can see the pen is getting more and more close, more and more horizontal. So the slope is decreasing. That means the electric field strength is decreasing from this point to this point. But will the electric field strength positive or negative? This slope will have a negative gradient. Multiply by minus sign, you will get a positive gradient. So that means electric field strength is positive and it's decreasing from 12 centimeter to 25 centimeter. So electric field strength is positive and decreasing. So according to F equal QE, Q is the charge that is moving from A to B, and electric field strength is decreasing, but it is positive. So force is going to be along the direction of motion and force is decreasing. So according to ME, F equal MA, the acceleration will be along the direction of motion and the acceleration is decreasing. So speed will increase when it moves from x equal 12 centimeter to 25 centimeters. Speed will increase. Why? The electrostatic force is along the direction of motion. So acceleration is along the direction of motion. Okay, I hope you understood. So speed will increase from 12 centimeter to 25 centimeter. Right. So that part we answer. So we can say speed is increasing from 12 centimeter to 25 centimeter. And also rate of increase is decreasing because slope is decreasing. Rate of increase of speed is decreasing. That means, what do you mean by rate of increase of speed? Acceleration is decreasing. Acceleration is decreasing. Why? Electric field strength is decreasing. Slope is decreasing. Electric field strength is decreasing. Electric field strength decreasing means acceleration is decreasing. You can answer first part like that. Okay, 26 centimeter is the lowest point, and at that point the slope is 0, the tangent is 0. But we know that the particle will have the maximum speed at the end of the acceleration. Remember that. Okay, in mechanics, something is accelerating. When will it have the something is accelerating, then moving at constant speed? Something like this. When we say the velocity or the speed will be the maximum at the end of the acceleration. So until 26 centimeter, it is accelerating. So at 26 centimeter, it will have the maximum speed. So answer for this one is at 26 centimeter, it will have maximum speed. Okay, I can say maximum speed occurs at 26 centimeter. Then 27 centimeter to 31 centimeter, that is somewhere here, 27 to 30, so in this part. Okay, so there you can see again, the slope is increasing, the tangent will increase, the gradient of the tangent is going to increase, right? So gradient of the tangent is going to increase means magnitude of E is increasing, but the gradient is positive multiplied by negative. That means the electric field strength is going to be negative and increasing. What does it mean? Negative and increasing means the direction of the electric field strength is going to be opposite to the direction of velocity. It had a maximum speed here, so somewhere 26 centimeters, somewhere here, right? So this is the point 26 centimeter. It gained the maximum speed. So when it moves beyond it, it's going to experience electrostatic force opposite to the direction of velocity because the slope is negative. The slope is positive. When you multiply by minus sign, the electric field strength is going to have a negative value. That means acceleration is going to have a negative value. That means the particle is going to decelerate. Okay, the particle is going to decelerate when it moves from 27 centimeter to 31 centimeter. It will decelerate and the deceleration will increase. Careful, the deceleration will increase. So rate of decrease in speed will increase. Rate at which the speed decreases will increase because the slope is increasing. Electric field strength is increasing, which is in opposite sign because minus, this is positive gradient multiplied by minus. So electric field strength is opposite. So acceleration will be opposite to the direction of velocity. So it's going to decelerate and the deceleration will increase. That's the answer for 27 to 31. It will decelerate and the deceleration will increase. Right, at 32 centimeter, at this point, say if you draw a slope here, still it's decelerating. So you can say at 32 centimeter, still it is slowing down or decelerating. Okay, at 32 centimeters, still it is decelerating. That is the answer for this part of question number 2. Okay, so still we are doing the question number 2, page number 4 in my worksheet. You can download it from Google Drive, the description part, all the instructions are given. Right, okay. Now the question number 2, B part, second, right? So they are saying a particle has a charge, page number 4 in my worksheet. I am doing page number 4. The particle has charge of 3.2 10 to the power minus 19 coulomb, 3.2 10 to the power minus 19 coulomb, and its mass is given 6.6 into 10 to the power minus 27 kilogram. Calculate the maximum speed of the particle. Okay, I told just now maximum speed will occur at the end of the acceleration. So when it moves from this point to this point, it is accelerating. So it will have the maximum speed at this point. Okay, so it's released from rest. Okay, so that already mentioned in the previous part of the question. So I can say work done W equal Q times delta V. So the particle is moving from higher potential to lower potential. I told that if a particle moves from A to B, A and B are 2 points. The potential here is VA, this is VB. The work done, the potential difference is given by delta V. If it moves from A to B, the potential difference is given by VB minus VA. And the work done should be W equal Q times VB minus VA. Now, a positively charged particle means you have to put positive sign. If it is a negatively charged particle, substitute negative sign, right? So here, if you get work done as a positive quantity, that means the particle will lose its kinetic energy and gaining gravitational potential energy. If the work done becomes negative and you include the sign of the charge, right? Q is the charge which is moving from A to B. Potential of A is VA. Potential of B is VB. Potential difference is given by VB minus EA. So when you find if you get work done, negative work done, that means the particle is losing kinetic energy. Sorry, particle is gaining kinetic energy and losing electric potential energy. That means electric field is doing work. If you get positive answer, that means particle is gaining electrical potential energy and losing kinetic energy. Work is required to move against the field, right? So here it's moving from this point to this point. So obviously we know that already explained it's accelerating. So I don't need to consider all these things, but if you want, you can consider that. I'll show that. And you find the work done. Look at here where it moves from this point to this point. If you find the work done, that is Q is given as a positive quantity, that is 3.2 into 10 to the power minus 19. Potential difference is moving from this point to this point. So this potential minus this potential, that is 1.43 minus 2.14 into 10 to the power 4, right? Now solve it. You will get the answer. That will be a negative work done. Okay, solve it. When you solve, you will get a negative work done. Okay, so you can see that the work done is a negative quantity. So W equal QV. So charge is given. This is the potential difference. And the work done is a negative quantity. That means what's happening there? The particle is gaining kinetic energy. So because it's gaining kinetic energy, its speed will increase. Initially, it was at rest here. So I can say this work done equal gaining kinetic energy, that is half mv squared minus it was at rest is equal to gaining kinetic energy is equal to the work done by the electric potential, that is 2.272 10 to the power minus 15. So half into the mass is 6.6 10 to the power minus 27, right, into V squared equal 2.272 10 to the power minus 15. Solve it for V, you will get answer 8.3 10 to the power 5 meter per second. That will be the maximum speed where it occurs at 26 centimeters. Okay, but if you are dealing with just numerical value, and if you are not interested about finding out whether it's gaining or losing kinetic energy, just you can use half mv squared equal qv. That's the way the mark scheme is given. They are not analyzing whether it's gaining kinetic energy or losing kinetic energy. We can find out when you know the potentials at different points, you can find out whether the particle is going to gain kinetic energy or lose kinetic energy by finding the work done by using the W equal Q delta V, and delta V potential of the final point minus potential of the initial point. You should include the sign of the charge. If you get negative work done, that means gaining kinetic energy, losing electrical potential energy. That's the meaning of it. If you are interested, you learn this way. Otherwise, just you can do work done equal half QV, Q times delta V equal half mv squared minus half mu squared. You will get the same answer in terms of numerical values. Okay, question number 3, page number 5, 8 part. State what is meant by electric field. You can say electric field means region where a charge experiences electrostatic force. Region where a charge experiences electrostatic force. That's the question number 3, part A answer. Okay, question number B, question number 3, part B. This graph grid is given as figure 5.1. So an isolated solid metal sphere has a radius capital R. The charge on the sphere is plus Q and the electric field strength at its surface is capital A. So you know if it is solid metal sphere, inside the sphere, the electric field strength will be equal to 0 because inside the metal sphere already the charges are displaced, they are at rest, so they don't experience any electrostatic force. So F equal QE, F equals 0 means E must be equal to 0 inside the conductor, right? So on the figure 5.1, draw a line to show show the variation of the electric field strength with distance x from the center of the solid sphere for values of x from 0 to x equal 3r. So they are measuring from the center. Since they are measuring from the center, the initial electric field strength must be equal to 0 initially. So up to R, the electric field strength must be equal to 0. So on the surface, they are saying electric field strength is E. So at R, the electric field strength should be equal to E. So I can draw this by a solid line. Right. Now what happens? We know we learned that we can assume the whole charge is concentrated at the center. So E equal KQ over R squared. So at 2R, that I can say E1 equal KQ over 2R all things squared, that is equal to 1/4 of KQ over R squared. That is 1/4 of, this is E, I can substitute this E. So E by 4, that is 0.25. So at 0.25, 2R, this is a coordinate. Same way, at 3R, I can say E2 is equal to KQ over 3R all things squared. That's going to be 1 over 9 KQ over R squared. KQ over R squared, I can substitute E. So at 3R distance from the center, E2 will be E by 9. So E by 9, we can take it, it's almost equal to 0.11. So it's great. You can take the value somewhere here, 0.11. Okay, you take it from the graph, the great lines. Okay, then connect this as a curve, not a straight line. So the graph will be this shape. Okay, that's the answer for the question number 3, B part. Okay. Question number 3, C part, page number 5 on my worksheet. The sphere in B has radius 0.26 meters. Electrical breakdown, that is a spark, is called electrical breakdown, occurs when the electric field strength at the surface of the sphere exceeds 2.0 10 to the power 6 volt per meter. Right? That's electric field strength. Volt per meter is a unit of electric field strength. Determine the maximum charge that can be stored on the sphere before electrical breakdown occurs means. So C part, question number 3. We know the electric field strength for a sphere is given by E equal KQ over R squared. We can assume the whole charge is concentrated at the center. So On the surface is given the electric field strength that can be the maximum without any breakdown is 2.0 10 to the power 6. K, I can take 9 into 10 to the power 9. They ask you to find the maximum Q because this is the maximum field strength that can be prevented without any spark, right? The radius is given, that is 0.26 squared. Solve it and you will find the maximum charge that can be on the surface just before breakdown, right? So you will get 1.5 10 to the power 1.5 10 to the power minus 5 coulomb. Okay, question number 4, page number 6 on my worksheet. You can download the worksheet from the Google Drive. Please check the description of this video. All the instructions are given there. Okay, question number 4. They are saying two solid metal spheres A and B have equal radii and are in vacuum. Their centers are 15 centimeter apart. The diagram is given. Sphere A has a charge of plus 3 picocoulomb and this is 12 plus 12 picocoulomb. The arrangement is illustrated in figure 5.1. This is indicated as 5.1 figure. Point P lies on the line joining the centers of the spheres and is a distance of 5 centimeter from the center of sphere A. Suggest why the electric field strength in both spheres is zero. Actually, you know they are conductors. They carry static electricity, that is stationary charges. So charges should not experience any electrostatic force inside the sphere. So if they don't experience any electrostatic force inside the sphere, they should not have any movement, so they should not have any forces. Therefore, accord F equals QE, F equals 0, so E equals 0. Understand? So once again, they are conducting spheres. They have delocalized electrons. So those delocalized electrons should not move. That means they should not experience any electrostatic force inside the sphere. So according to equal QE, F must be 0. Therefore, E must be 0 inside the sphere, right? That is the A part of question number 4. B part, show that the electric field strength is 0 at point P. So that means point P is a null point. So if I keep a positive test charge, you know that this will repel. So I can say E1 is this direction. So that, like this also carrying positive charge. So that will repel. E2 will be towards left. So at point P, if I show E1 equal E2 or E1 minus E2 is the resultant field strength, that is equal to 0 because direction is defined by the positive test charge. So these directions I obtain by using positive test charge. When I keep it, this will repel, that is E1, this is repel, that is E2. So the net field strength at point P, I can say that is question number 4, B part. The electric field strength at P equal E1 minus E2. So E1 equal K Q1 over R1 square plus minus K Q2 over R2 squared. So 9 into 10 to the power 9. Q1 3 picocoulomb, 3 into 10 to the power minus 12. R1 is 5 centimeter, 0.05 squared minus Q2 is 12 picocoulomb, 12 into 10 to the power minus 12 divided by that distance of P from the center of B. You know that charges are concentrated at the center. We can assume like that. Several times I explained that. So that distance will be 10 centimeters from the center of B. The distance of P is 10 centimeters. So 0.1 squared. Solve it, you will get 0. Yeah, that is 0.1 square because this is 10 centimeter. So 0.1 square, I wrote it earlier, 0.12, that square, I put it here. Okay, 0.1 squared, right? So you'll get electric field strength, that is 0. Okay, part C, page number 6. Same question. Question number 4, part C. Calculate the electric potential at P. So electric potential is a scalar quantity. So I can say electric potential at P equal, summation of potential of this one and this one. So I can say K Q1 over R1 plus K Q2 over R2. So 9 into 10 to the power 9, I took common. Q1 is 3 into 10 to the power minus 12 pico. R1 is 0.05 plus. Okay, it is a scalar quantity, so no direction, just add it. Q2 is 12 into 10 to the power minus 12 over, that distance is 10 centimeters, so 0.10. Solve it. You will get the answer in volt. So the answer will be equal to 1.62 volt. Okay, so next part, that is part D. A silver 107 nucleus, that is Ag107, that is mass number is 107, atomic number is 47, so number of protons is 47, has a speed v when it is a long distance from point A. Okay, when it is long distance from point B, it has a speed of v. Use your answer in C. So we found the potential in part C, right? Use your answer in C to calculate the minimum value of V such that the nucleus can reach point P. Okay, so when the nucleus is initially at a distance P, long distance. So long distance means the potential is inversely proportional to distance. So we should take the potential at that point. Far distance is equal to 0. So when the positively charged this silver nucleus, when it approaches, it's going to experience opposing force. So it's going to slow down and it will finally come to rest because they're asking to find the minimum speed. Means at point P also, it should become just rest. So far distance, where the potential equal to 0, the speed is v. What should be the minimum speed there to reach the point P means at point P, the speed should become equal to 0. So at far distance, potential is equal to 0. At this point, we found the potential. So we know that when it moves from far distance to this point, it's going to lose its kinetic energy. So when it loses its kinetic energy, it will do work against the electric potential, or it's going to gain electrical potential energy. So according to my way of teaching, I told that earlier, if you are finding the work done, that is equal to Q into delta V. Delta V means potential of the final point minus potential of the initial point. Take it like this. So potential of the final point minus potential of the initial point into multiplied by the charge. When you get positive work done, that means again the moving charge particle will lose its kinetic energy and gain electrical potential energy. When you solve this one, including the sign of charge by using delta V as this way, if you get a negative answer for the work done, that means the particle is gaining kinetic energy and losing electrical potential energy. So in this question, it's moving from far distance where the electrical potential is equal to 0, right? And at the point P, the electrical potential, we know that it's moving from far distance to point P. So I should write Vp is reaching the point P, Vp minus V far distance, V far distance. So that is charge of the particle. We know that it consists of 47 protons. So 47 into 1.6 into 10 to the power minus 19. That's the charge of the silver nucleus. Vp, we just found it in the previous part. That is 1.62 minus far distance means potential is equal to 0. Solve it, you will get positive work done. That means it's losing kinetic energy. So certainly it will just come to rest at point B for the initial minimum speed at far distance. Okay, solve this one. Okay, so this is the work done, that is positive work done. Positive work that means the particle will lose kinetic energy and gain electrical potential energy. So I can say loss in kinetic energy equal work done is the gain in electrical potential energy. So loss in kinetic energy equal gain in electrical potential energy. You can say all work done. So loss in kinetic energy means half mu square, the initial speed minus final speed. So final speed is 0 because it's just reaching the point P is equal to work done 1.22 10 to the power minus 17. So half into, okay, mass is not given, but we know the mass number of the silver nucleus is 107. So silver nucleus consists of protons and neutrons. Mass of proton is almost equal to mass of neutron. That is, mass of proton is 1.66 10 to the power minus 27. That is given in the data sheet in the exam paper, right? I didn't give this in my worksheet, but normally in the exam paper, it's given as a the data sheet. So the mass is 107 into 1.66 10 to the power minus 27 into the initial speed at far distance is given as v. So I'm using v squared. Okay, initial speed is v squared. Is moving from initial point is far distance. Finally, at point P, the speed is 0 equal to 1.22 10 to the power minus 2017. Solve it. You will get the v. You will get 1.2 10 to the power 4. Okay, students have confusion. When it moves from one point to another point in electric field, will it gain kinetic energy, or will the speed increase, or will it lose kinetic energy? Will the speed decrease? Is a common confusion students have. So that's the reason I made video lesson 8. I'm explaining there about all these negative potential, positive potential, negative work done, positive work done, negative potential energy, positive potential energy. What do they mean, right? So those who have confusion, please go through that particular video. Okay, so I discussed up to question 1 to question 4 in my worksheet. So then the other questions, question 5 to 7 will be discussed in the next video. Okay, so I'll stop this video. Then we'll continue with the next, in the next video, the other questions.